All right, let's jump right in. You ever stare at a bunch of numbers and just get that feeling? That sense that there's a secret pattern locked away inside? Well, today we're going to grab the key. We're going to look at a really simple but seriously powerful technique for cracking that very code.
So take a look at this. These dots, they're not just random, and they're definitely not making a straight line. You can see they're tracing this perfect, sweeping curve upwards. There's a rule here, some secret logic that's connecting them all. The big question is, what is it?
To figure this out, we're going to put on our detective hats. Our mission, if we choose to accept it, is to find the one specific mathematical function, the hidden rule, that perfectly explains what's going on with these points. And here is our case file. This table, this is all the evidence we've got. You can see when x is 0, y is 2. When x is 1, y is 3. Then at x equals 2, y jumps up to 6. You can see the y values are growing, but they're picking up speed, right? They're growing faster and faster. That's our very first clue. Every good detective needs a toolkit, and ours has this one awesome tool that's just perfect for this kind of mystery. It's called the method of finite differences. And trust me, it's going to help us uncover the pattern that's hiding in plain sight. So, what in the world are finite differences? It sounds complicated, but it's really not. It's just a fancy way of saying we're going to find the difference between the y values that are next to each other. We just subtract. But the real magic happens when you do it again and again. It's like peeling back the layers of an onion to find the core truth. Okay, toolkit is open, case file is on the desk. The investigation is officially on. Let's put this method to work and start hunting for some clues. Step 1, we calculate the first differences. It's super simple. We take the second y value, which is 3, and subtract the first one, 2. That gives us 1. Then we do 6 minus 3, which is 3. Next up, 11 minus 6 is 5, and 18 minus 11 is 7. Now look at that new column we just made. 1, 3, 5, 7. I mean, that's a pattern for sure, but it's not a constant number. The plot thickens. So, our first attempt didn't give us a constant. What does that tell us? Well, it tells us this isn't a simple straight line. If it were, all those numbers would have been exactly the same. So what's a good detective to do? We got to dig deeper. Let's do just that. Step 2, we're going to do the exact same thing again, but this time we're doing it on that new column we just made, the first differences. Okay, so 3 minus 1 gives us 2. 5 minus 3 is also 2. And 7 minus 5, yep, you guessed it, it's 2. Bingo, we hit a constant. This is the breakthrough, the aha moment we've been looking for. That constant number, that 2, is the golden clue that cracks this entire case wide open. We found the signal in all that noise. So now let's talk about what this big reveal actually means. So yeah, it all comes down to this one little number, 2. This is what our whole investigation has been pointing to. It might not look like much, but that constant value tells us absolutely everything we need to know about the real nature of our original data. And here's the cool part, the core principle of this whole thing. Because it took us 2 rounds of finding differences to get a constant, that means our data is described by a second-degree polynomial. It's that simple. In other words, the secret function is a quadratic, something that looks like y equals ax squared plus bx plus c. We've just identified the function's family. And this isn't just a one-time trick. This is a fundamental rule in mathematics. The source material spells it out for us. This method works for identifying the degree of any polynomial data. If we had found a constant on the very first try, it would have been a first-degree polynomial, a straight line. If it took 3 tries, a third-degree or cubic function. It's a beautifully reliable system. So, case closed, right? But why does any of this matter outside of a neat little math puzzle? Let's zoom out and look at the bigger picture here and see how we go from just having some numbers to building a really useful model. So here's our method, our 4-step playbook. You line up your data, you calculate the differences, you keep doing that until they're constant. And then, the number of steps you took, that's the degree of your polynomial. It's this elegant, repeatable process that you can use on any dataset that behaves this way. And let's not forget the end game here. The whole point is to create a mathematical model. We're not just finding a pattern for the fun of it. We're building a function that actually describes a real relationship. Now that we know for sure that it's a second-degree polynomial, we can use other tools to find the exact equation, and that gives us a really powerful model. And this is why it's so important. These models are literally how we make sense of the world. They help us predict things, like population growth, or where a rocket's going to land. They let us analyze business sales trends. They even describe the laws of physics, like the path of a ball thrown through the air. By turning a bunch of mysterious data points into a clear mathematical model, we get the power to understand, to predict, and even to shape the world around us. So the next time you see a pattern out in the wild, the arc of a basketball shot, the way a plant grows toward the sun, anything really, just remember this. There's probably a mathematical code hiding right under the surface. And it just leaves you with one question. What patterns all around you are just waiting to be discovered?